Yeah. Yes, good morning, everyone. Good morning, Professor Zhu Yan.
Good
We are
morning.
up. We'll start the lecture 2 today.
I didn't understand that.
Handing over to the professor. Please, I'll first stop the sharing the screen. You can go ahead, Professor.
Okay. Wait a second. I'm sharing my screen. Screen. All right. Can you see the screen now? Can you see the screen now?
Yes, Professor.
Okay. Good. Okay. Good morning, participants. Professor Siva Kumar. Very good morning to all of you. So today is the second day of our GIAN lecture, Renewable Energy Systems in Smart Grid. Today, according to the teaching schedule, we will continue to introduce the energy internet. But before that, I would like to have a very quick review of the lecture yesterday when we have introduced the smart grid. We also touched a bit on the energy internet, especially for some demonstration projects, right? So for the smart grid, remember yesterday we have talked about this general high-level illustration. So basically, for the smart grid, at the generation side, we have a high-level penetration of the renewables, including the wind power and the solar power. So they are very different from the traditional thermal power plant, hydropower plant, or even nuclear power plant, because these renewables have no emission, right? No carbon emission, no pollutions. So that is one technical feature of the smart grid. And at the demand side, customer side, the smart grid will see new types of the low demand, such as the electrical vehicles, and also flexible load. Right, this flexible load can support demand response. For example, if there is a need from the power grid operation perspective, the demand can increase or decrease via power demand. And taking the electrical vehicle as the example, if there is a need, we can schedule the charging time of the vehicles so as to support the power system operation. And besides, the electrical vehicle may also be able to discharge their power to support the grid. This is also known as the vehicle to grid, V2G function. And besides, you can see at the demand side, we may also install energy storage systems, which can also support the utilization of the renewable energies, because wind and the solar power, they are always fluctuating, intermittent, right? So the energy storage system can charge and discharge to compensate this power output fluctuation. So that's why, in the demand side, we will see these new elements. Well, on top of it, you may also remember we have advanced ICT technologies, including the smart meters installed at the household level, which can collect the power consumption data instead of just the energy meter, right? And besides, we also install the signal measurement unit, which is a very advanced technology that can measure synchronized and real-time phasor values of the grid. And you can see this phasor measurement unit, PMUs, they are synchronized by satellite GPS, so that the measurements are time synchronized. So these values can support the dynamic analysis and the dynamic control of the power grid. So let's just make the final review of the smart grid. Remember, we have three major features. Number one is renewable energy resources. Number two is the more participants from the demand side. Number three is more advanced information and communication technologies. So everybody, please remember these three major features of a smart grid. Okay. Then yesterday we have also briefly introduced the energy internet concept, which is actually the next step of the smart grid. Remember this graph, right? Very importantly, the difference is that the energy storage will also incorporate other energy systems, including the transportation systems and the gas networks. Okay, so compared with the smart grid, energy internet is more complex and more advanced. We have yesterday compared their differences in these different aspects in terms of the penetration of renewables, the energy generation, right, the physical systems, the ICT networks, the energy carrier transportation, as well as the control of the whole system. So energy internet is much more advanced than the smart grid. Okay, so yesterday we have briefly introduced this concept. And remember, yesterday we very quickly go through these projects ongoing in USA, Europe, Australia, China, and also the one in Singapore. So today I'm going to talk more about our projects in Singapore related to energy internet, so as to give you a better understanding and more comprehensive knowledge about this new concept. So this is a general content and topic of this morning. And in the afternoon, we are going to introduce the advanced metering infrastructure and the smart meter, which is the third, right, technical features of the smart grid. Okay, so I would like to go through the energy internet, talking more about the one of our very leading research project happening in the Singapore. Okay, so wait a second, please. I will show these slides to you. A very important a very important feature of the energy internet is to combine the multiple energy systems, right? Especially the thermal and gas networks. So actually, in our READS project, yesterday I have briefly introduced this one, right? The so-called Renewable Energy Integration Demonstrator for Singapore. This project is actually have energy internet component because we have been developing an energy management system for the multi-energy microgrid. Okay, so you can see that this system actually is built up in this island, apart from our Singapore main island, about 10 kilometers. Okay, this project actually is industry collaboration, industry and academia collaboration. So we actually have many companies collaborating with us. And remember, yesterday we have introduced this structure. So in this research and development platform, we have actually built up 8 individual small systems called microgrid. Okay, Then in the first phase, we have built up 4 independent small microgrids with 500 kilowatt to 1 megawatt each. Then in the second phase, we have built another 4 microgrid systems with a smaller capacity ranging from 100 kilowatt to 250 kilowatt each. So the total capacity of the whole system is about 3.5 megawatt. Okay, not that big, but not that very small, because in Singapore, the peak power demand is around 8,000 megawatt. Okay, 8,000 megawatt. So if you look into this system, you can see that we have a mix of different energy production and energy consumption sources. We have solar PV, of course, because Singapore is in the tropical region, so we have abundant solar irradiance. However, Singapore does not have much wind resources because we are in the equator part. You know, in the equator, there is very little wind sources. However, this wind turbine is mainly for the low-speed wind power generation technology. So this is actually one of the largest wind turbine in the whole country. Okay, it is for the experimental purposes. And besides, we also have a marine power generation, which make uses of the wave of the sea to generate electricity. Okay, so we have quite a mix of renewable power. And in terms of the load, we have a unlined load, residential, commercial, as well as the so-called SME. SME is a kind of a factory. This factory actually consumes a lot of heating energy. Okay, so from the whole system, we are generating both electricity as well as the heating. So later I will introduce how these different energies are coordinated in the energy internet pattern. Besides, we have other industry loads, including this desalinization of the water, okay, which certainly have flexibility. And very importantly, we have a mix of energy storage technologies, including the batteries, including the flow batteries, redox, lithium batteries. We have mechanical energy storage flywheels. We have electrical energy storage supercapacitor. And we have the power to gas electrolyzer, which can generate hydrogen from the water and the electricity. And in order to make use of this hydrogen, we also have a fuel cell. Okay, fuel cell can directly convert the hydrogen into the electricity and the water, and in the meantime, it will produce heat. Okay, so this heat from the fuel cell will be consumed by one of the load in the island called SME, Smart Multi-Energy System. Okay, now, as I said, we have 8 individual microgrid systems. Actually, all these microgrid systems, they are interconnected together as a cluster. Now, yesterday I also touched a bit. We have different companies joining with us, right? Some companies are focusing on the solar panels, right? This Sunsip is a local company. RES is the one from Thailand. China Solar is from China. Okay. The energy storage system, we have Samsung, we have Murata from Japan, we have DP, Dura Power in Singapore, we have NG from France. They are all investing different energy storage technologies. And in terms of the diesel generator, okay, we have MTU, which is a sub-company of Rolls-Royce Electrical. Okay. They are actually installing a diesel generation set on the island as the manpower generation sources. And certainly in order to coordinate and integrate this microgrid system, we need to have the microgrid controller and the energy management system. So for my research group, I'm collaborating with Rolls-Royce Electrical and EDF Lab. EDF is a power utility company in Europe, headquartered in France. They also have a research lab in Singapore, so we are collaborating with them to develop this system energy management and the control system as well. So this is a general picture for the whole project. I hope you have a good understanding of it. Now you can see that these individual microgrid systems, they are actually invested, operated, and owned by different companies. So our university is a coordinator of these 8 microgrids. You can see this is a general electrical structure. We have this 6.6 kilowatt linkage bus. So all the individual microgrid systems are connected there. And our university is running microgrid 0. Other companies are running microgrid 1 to 8, okay, with a different focus. Now, this system has already been introduced in this article. If you are interested, you can take a look there with more details. So these pictures yesterday I have already shown to you, so I will just skip it. But I would like to talk more on these research problems. Okay, because you know this whole project is a research and a development platform. So on this platform, our focus has a lot of are very diverse. First of all, we need to look at the control interoperability of different microgrid system, and certainly we need to have a very reliable communication protocol, so on and so forth. And besides, you can see we can collect many data from this 8 microgrid system. Then we can perform data analytics, and we can use AI, artificial intelligence, to do the asset control and the maintenance. Okay, and very importantly, energy storage is a critical component. That's why tomorrow I will introduce energy storage technologies and their applications. So in this system, we also develop an energy storage management system to control the charging and discharging of the batteries, fuel cells, and the supercapacitors, okay, to manage the whole system. And of course, we need to optimize the whole system, the microgrid system, including the electricity and the thermal energy demand. Okay, and the power grid dynamics. Okay, because we have converters interfacing the wind turbine, solar power, and the energy storage system. So the dynamics of the grid could be very complex. Yesterday, we have briefly introduced how the power converters will change the dynamic behavior of the grid. So one of the very important topic for this platform is at the power system, power grid dynamics analysis. Okay, and new technologies, especially power electronics, right? Power converters, new power converter topologies, new control strategies, so on and so forth, are also being researched. Besides, we also look at the reliability and the resilience of the system. Okay, for such an interconnected microgrid system, how can we improve the general reliability? Remember yesterday we talked about the reliability indexes, the SID and the SIFI, right? So SID, SIFI are measure of how long of the power outage is over a year, and how many times of a power outage will happen in a system. So we also need to look at these reliability indexes. And last but not least, the economic modeling and demand response, energy trading, these are all about the market participation from the demand side. Because one of the final objective is to take the whole microgrid system as a single controllable participant in Singapore's electricity market. So we can provide demand response and we can trade the energy with the main grid. So these are actually very realistic functions of the smart grid and the energy storage, energy internet, right? Remember yesterday when we briefly introduced energy internet, one of the objectives is to freely share the electricity with your neighbors or even with other market participants. So the energy trading is one important dimension for energy internet. And in order to do the decentralized energy trading, we may have to use blockchain technology. So in our research group, my students are building a private blockchain to realize this, energy trading at the lab scale. Okay, so that is something about the project we are running at this moment. And you can see here, we also are collaborating with these companies to make the whole system as a market participant and provide these grid ancillary services. Okay, grid ancillary service, because in Singapore we have a wholesale market, wholesale electricity market. We are the participants can provide this ancillary service, including the peak shaving, load leveling, power quality support, frequency support, spinning reserve, and congestion relief, so on and so forth. And by participating in this wholesale market, the participant certainly can gain revenues, right? This is certainly the second feature of the smart grid, which is to encourage more participation from the demand side. So you can see that this whole REITs project is a very comprehensive demonstration of the smart grid and energy internet technology. Now, let me go to the so-called system operation perspective to let you know more about the operation of the energy internet, especially considering multiple energy carriers. Okay, so I suppose you have some fundamental knowledge about these different components, all right? So this is a kind of illustration of one of the microgrid system, as I just mentioned, right? We have the wind turbine, we have the solar power, we have the batteries, we have the electrical vehicles, we have the diesel generators, we have the fuel cells, right? Everything is there. Now this system is a kind of clustered system, which is connected with the main grid through this point of coupling, PCC. Now this PCC can be closed and can be opened. When it closed, this whole system is connected to the main grid. So we can import electricity from the main grid, and in the meantime, we can also sell electricity back to the grid. So that depends on the status of this PCC switch. Okay. Now, the question is, how can we dispatch and how can we operate this microgrid system by dispatching the controllable resources and also considering different parameters, including the renewable power output, which are uncontrollable. So here we need to have an understanding of the basic concept, including the control sources, parameters, power grid, network model, and the state variables. Now, if you look into this system, where are the controllable resources? Which means these resources can be fully dispatchable, fully controllable by the operator. Now, if we divide the sources into the active power and the reactive power sources, basically, the active power resources include the micro turbine, right? The micro turbine diesel generator. And this diesel generator, they can simultaneously produce electricity as well as the thermal energy. Okay. And besides, we have the energy storage system. This energy storage system, they can charge and discharge electricity, active power, right? And besides, we may also control the demand, control the flexible load. Okay, flexible load here. This flexible load means this load has a certain flexibility. For example, the electrical vehicles or the laundry machine. Let's take the laundry machine as an example. So for the laundry machine, sometimes the customers, they don't care about the timing of the operation of the laundry machine. So as long as the laundry job can be finished before a certain time. For example, for myself, usually I do my laundry in the evening, okay, I put my clothes into the laundry machine and I set a timer. So as long as this laundry job can be done before 11 p.m., I'm okay. I don't care when it is immediately running or not. So this laundry machine has a so-called time flexibility. Okay, we can schedule this laundry machine at different time periods to compensate, to take advantage of the dynamic electricity price or to take advantage of other electricity consumption within a household. Right? And besides, the electric vehicle is also maybe time flexible, because when we charge the electric vehicle, we don't care about when the vehicle is charged, but we need to make sure, okay, before next day early morning when I go to work, I need to make sure the vehicle is fully charged. I don't care when it is charged at 9 p.m. or 1 a.m. Right? I don't care about that. So these vehicles, electric vehicles, they also have flexibility. And this type of flexible load can be called demand response based load. They can respond to a certain kind of incentive or kind of control signal. Okay, so later on in the afternoon, when I introduce smart meters, I will introduce how the demand response will be achieved, okay, based on the smart meters. But generally speaking, my point is to let you understand how many active power resources in the system can be controllable. Okay, they can be controllable. And in the term of the reactive power, okay, reactive power is mainly concerned on the voltage regulation. Okay, so because we need to make sure the voltage magnitude of the buses stays within a certain limit, usually plus minus 0.05 per unit. Right? Then for the reactive power resources, traditionally we have capacitor banks. Okay, the capacitor banks can produce reactive power. And we also have the OLTC, the unload tap changer transformer, including as illustrated here. Right? This unload tap changer can adjust the voltage transformation ratio online. Okay, so if we found the voltage is a bit low, we can adjust the tap ratio to a higher step, so as to step up the voltage a bit. So by doing that, we can also regulate the voltage, and correspondingly, it it will lead to the reactive power consumption or balance. So OLTC, unload tap changers, are one of the reactive power sources. Okay, and what else do we have? Very importantly, we have the PV inverters. Okay, somebody may wonder, okay, why we include the PV inverters as reactive power sources? That is simply because the inverters are power electronics device. They are actually able to consume or even produce reactive power. Okay, so this is a very useful function of the inverters, especially for voltage regulation and voltage support. Because later on, I remember should be the last day when I talk about distributed generation, I will introduce issue caused by distributed generation resources, which is the voltage impact on the distribution grid. Okay, because the distributed generation, rooftop solar PV, the small wind turbine, their power output is always fluctuating. They will fluctuate the bus voltage as well. Okay, the question is, how can we mitigate this voltage fluctuation? Now we have to use these reactive power sources. Now, since the voltage fluctuation is caused by the PV system, so why not we make use of this PV's inverter to solve the problems caused by themselves? So this is a major, idea or motivation using the PV inverters as a reactive power source. So later on in the day 5, I will introduce more details on that. Okay, so these are so-called controllable sources. In mathematical perspective, we call it control variables, okay, because their values can be controlled. That's why it's called the control variables. And besides, for this system, what are the parameters? So parameters means these values are objective. Okay, they cannot be controlled. They cannot be changed. They are just objectively determined. Right? For example, the base load demand, right? The load demand, the inflexible load. This load cannot be changed. For example, the critical loads, let's say the hospital, right? The government offices, and let's say the railways, the railway system. These loads has no flexibility. We cannot change their timing and the power consumption amount. Unlike the flexible load, right? Demand response based load. These loads are kind of fixed. We cannot change them. So this load is considered as a parameter, okay, parameter of the system. And besides the wind and the solar PV power output, they are all parameters because they depends on the weather condition, right? The wind power depends on the wind speed, and the solar power depends on the solar irradiance. So we cannot control them. So these values are so-called objectively determined. We cannot control them at all. And furthermore, the electricity price, okay? The electricity price is determined by the market, by the electricity market, or kind of regulated by the government agencies, regulators. Okay, so this electricity price certainly cannot be controlled by the system. It cannot be controlled by the system. However, later on this afternoon, I will introduce from the system operation perspective, we actually are able to adjust the electricity price to the customer so that the customer can respond to the electricity price. Then indirectly, we are able to change the load demand. This is the so-called price-based demand response. So essentially, the idea is to change the load. Now, this afternoon, I will introduce more on that. But here, what you need to know is that, okay, for the system, for the multi-energy system operation, the load, the renewable power output, the electricity price, they are all objectively given. We cannot change them. And besides, the network parameters, okay, the electric network parameters, the resistance, reactance, capacitance, certainly they are physical parameters. We cannot change them, right? So they are all parameters. They are all parameters. Now, after that, we have talked about the resources of the components in the system. What else do we have? As a system, as a power grid, certainly we need to model its network. Okay? We need to model its power flow of the system. So for this system, we have different models to use. The original one could be a full power flow model. I suppose many of the students, participants, you have already learned the power flow, right, of a power grid. But apart from the full AC power flow, for the microgrid multi-energy system, we can also use the linearized distribution flow model. And this one I will also introduce in day 5. But here, just to give you an initial idea. And besides, in mathematical area, we also develop a second-order COM programming model. This is an advanced mathematical model to characterize the power flow of the distribution grid. So these models can also be used in this regard. And when we operate this multi-energy system, what are state variables? State variable means these values can these values are kind of variable. However, they are not directly controlled by us. For example, bus voltage. We cannot directly control the bus voltage, right? But we can change the capacitor banks. We can change OLTC tap ratios. We can change the PV inverter's power, reactive power output, so as to indirectly change the bus voltage. That's why it is called state variable, because its value depends on other control variables. Okay. And the branch power flow. Okay, the power flow along a branch. This one is not directly controllable. We cannot set the power flow from one end to the other end. This is not doable. Okay, because the power grid is a complex electrical networks. It has to follow the KCL, Kirchhoff current law, and the Kirchhoff voltage law. So if you want to change the power flow, you have to change the control variables. That's why this power flow is called state variable as well. And last but not least, the power exchange with the main grid. Okay, if we want to import more power from the main grid, or if we want to sell the electricity back to the grid, we cannot directly control this value. Okay, we cannot directly control the power exchange value because, as I said, the electricity network is need to follow the physical law, right? They need to follow the KCL, the total power in current injection equals to the total power output. So this power exchange is also a state variable. We can only control or schedule the control resources to change it. So this is the main idea. Okay, you have to understand this main idea before I introduce later on the demand response supported by smart meter this afternoon, and also energy storage applications in day 3, because energy storage is to charge and discharge so as to change all of this bus voltage, branch flow, power exchange. Okay, so that is the main idea. Okay, now I think we can have maybe a 5 to 10 minutes break before we move to the next part. All right, so please come back in 10 minutes. Okay, in 10 minutes, please come back.
Okay.
Okay. Hello, everyone. So let's go back. Okay, so just now we have introduced the basic concept of the controllable resources in a system, parameters of a system, as well as state variables of a system. And we also briefly introduce how can we model the network in terms of the power flow. Now, here I would like to introduce a specific example for the energy internet realization. Okay, remember, energy internet is integration of multiple energy carriers, including the electricity networks and the thermal networks. Right? So in this, our demonstration project, we are actually developing this multi-energy microgrid system. Because just now I have introduced, we have quite a good mix of different sources. For the microturbine, we are using the Rolls-Royce diesel generator. It can simultaneously, and besides, we have also placed the heat recovery unit and the absorption chiller unit. This heat recovery unit and absorption chiller can make use of the vast heat from the microturbine when it is producing electricity. Now, this vast heat is converted into heat energy and cooling energy. Okay? And besides, we have also the energy storage systems for heating and the cooling storage. So here we have ice storage tank and the heat storage tank. This can store this cooling and heating energy when they cannot be fully consumed. Okay, and besides, we have traditionally we have these electricity generation units, wind turbine, PV panel, and the battery storage for electricity. And besides, remember we have the fuel cell, right? The fuel cell can generate the electricity as well. And in the meantime, it actually can also produce heat. But in this case, we do not make use of it because the major heat comes from the microturbine. Okay. Now, for the load, we have different types of the load. We have the power load, we have the heat load, we have the cooling load. Especially in Singapore, where the average temperature is always high, around 30 degrees something. So the cooling demand in Singapore is very high. Okay, so you can see that, and the whole system is also connected with the main grid. So in such a system, you can see we have three different energy carriers: the power grid, the heat, and the cooling. Okay, they are denoted with different lines: the solid line, long dash line, and short dash line. Okay. Now you can see that. And besides, we have also placed the electric boiler and the electric chiller. This electric boiler is to generate the heat using electricity. And similarly, electric chiller is to generate the cooling energy using the electricity. You can just take this chiller as a air conditioner, okay? But it's a big size. The size is much bigger, so it is a chiller power plant, chiller plant. Now, you can see this system is a multi-energy system. That's why yesterday, when I firstly introduced energy internet, remember what I have said. Energy internet, they may have different meanings. They may have different realizations. Okay, sometimes we can combine the power grid with the energy, transportation grid and focusing on the electric vehicle side. And sometimes we consider the power grid and the thermal network and focusing on the cooling and energy side. Now, in our project at NTU, we focus on the latter case because, as I said, in Singapore, the cooling demand shares a very high percentage for the total energy consumption. Okay, so in addition to the traditional air conditioner, we can also make use of this assumption chiller from the micro turbine to produce the cooling energy. So in such a case, we can form up this microgrid, multi-energy microgrid. Okay, we can form up this multi-energy microgrid. And in fact, this concept was introduced in this paper of us. And this paper is very highly cited. Back to 2017, we have received the Web of Science Highly Cited Paper Award. Okay, paper award. So if you are interested, you can take a reference of this paper, and there are more details. But today, I will just give you a general idea about how this multi-energy system can be operated. Okay, so that apart from the high-level concept understanding of the energy internet, you know how the energy internet can be realized in real world. Okay, now for the multi-energy system, we certainly need to model the system, right? In order to operate, control it, we certainly need to have its model. For power grid, okay, for the power grid, we are already very familiar. We can use a power flow model to analyze, calculate the voltage, the power flow, active and reactive power. Just now, remember, I have introduced the dist flow model and the second order com model to characterize the power network, right? This part we are already very familiar. I suppose many of the students, if you are coming from the power engineering background, the power flow is a very fundamental subject, right, during your study. Now, for the multi-energy system, I think the major challenging part is on the thermal network. Okay, because for power engineering people, we only handle with the power, the electricity. We don't touch the heat. We don't touch the cooling, right? We don't touch the pipeline. We are looking at the cables, transmission line, electric conductors, but we don't deal with this thermal network in the past. Right? So in order to do the energy internet, we need to expand our knowledge set. So here we have to consider the heat network of the multi-energy system. Specifically, we need to look at the district heat network. Now, the district heat network means it is at the district level. It's not a large scale. For example, on our campus or for a community, for an industry park, this size of the scale can be considered as a district system. Now, the heat network is to connect these different heating loads together through the pipe line, through the pipe network. Now here, this is the illustration, right? We have the heat sources. This source can come from the micro turbine and can come from the fuel cell, even can come from the electric boiler, right? For the thermal energy. And for the cooling energy, the same, it can come from the cooling plant, right? The chiller plant. Now, these heat resources will be transmitted to the heat exchanger. Okay, to the heat exchanger. The heat exchanger will exchange the cooling or the heat with the customers. For example, this heat exchange can be in the form of the water, or can be in the form of the air. Right? The heat, let's say the very high temperature water will go through to this heat exchanger. A heat exchanger will go through the heat load and exchanging the heating from between the high temperature and the low temperature. And after that, the load will be supplied, we obtain the heat. And as a return, the heat exchanger, the original heat sources will have a lower temperature. And after that, it will return to the heat source. That's why here you can see we have the primary supply pipes and secondary supply pipes. One is going out, one is coming back. Okay, so in such a way, the heat is supplied from the source to the load. Now, another question is we have to model this pipeline. Okay, we need to consider the flowing speed of the heat water or the high temperature air. Okay, we need to consider the resistance of the heat flowing, and we need to consider the insulation, the loss during the heat transfer. Okay, so we have to model this pipeline. This pipeline certainly is a physics pipe, so we need to look at its dimension, we need to look at its insulation parameter, we need to look at its resistance, so on and so forth. So that is for the network side modeling. And besides, we have to model the load, the thermal load, right? Most of the thermal load come from the building, right? In terms of in Singapore's case, the thermal load comes from the cooling demand. But when we supply the cooling demand to a building, we need to consider its insulation, the thermal insulation, right? So here we have to model its thermal conduction of a building. Okay, when the building receives a certain amount of cooling, and considering its walls, its structures, its concrete, how much time will it take before the heating and cooling will be exhausted? Okay, so here we have to consider the thermal model of a building. I mean, at the load side. Now, after that, after we model this thermal network, we can couple it with the electricity network. This is the so-called coupled electrical thermal network. Right? Yesterday, remember, just now when we review the energy internet, we talk about the coupling of the electricity network and the transportation network. Right? For that type of coupled network, our concern is on the electrical vehicles charging, discharging with the power grid, and they are routing on the road. But here, if we are focusing on the thermal and cooling energy, we have to have this coupled electric and thermal network. Okay, and certainly the coupling point of the two networks is based on the combined cooling and heating power plant, CCHP, right? CCHP, the coupling point is this one, and this energy transfer unit, right? Electric boiler and the electric chiller. Okay. That's why these two networks can be coupled together. Okay. Then for the detailed modeling of the thermal network, we have presented them in this paper. Okay. In this paper, you can also refer it for more details if you are interested. Now, the next challenging part is how can we dispatch this coupled network, right? How can we dispatch this coupled network? Remember, just now we have introduced the control variables and the parameters and the state variables, right? So the general idea is that we can dispatch the controllable resources, okay, changing its setting point for power production, right? Thermal energy production. And for the energy storage, we can control its charging and discharging of electricity and the thermal energy. Okay, so in our project here, we have designed this so-called two-stage coordinated operation. Now, it sounds a bit complex, but generally speaking, the idea is for the thermal system and power system, the components, they have different responding speeds and they have different characteristics. Right? Clearly, for the electricity, right, the transmission speed is at the light speed, okay, is at the maximum speed. As long as the electricity is produced, we have to immediately consume it. Okay, so that is for electricity. But for the thermal energy, there is no need to immediately consume it because the inertia of the thermal energy is much, much longer, right? And the transmission speed of the heat water or the heat air is certainly not a light speed, right? They can be transmitted at a slow speed. So you can imagine that one is electricity, one is thermal energy. They have very, very different characteristics. How can we coordinate them? So considering this difference, we cannot combine them together directly. for operation, for dispatch. We should separate them together. Yeah, that's why here we introduce this two-stage coordinated operation. Okay. Two-stage means we divide the operation into two stages. One stage is only for the thermal energy. Okay, we dispatch this thermal energy over a long time horizon, covering a relatively longer time interval. Okay, that is for the slow responding thermal energy. And the second stage is for the electricity. The electricity certainly is, transmitted at the light speed. So we have to make sure the electric power supply and the demand are real-time balanced. So we dispatch the electricity as the second stage. Now, however, these two stages, they have to coordinate because the power generation, thermal multi-energy generation, come from the same unit, right? From the microturbine. When the microturbine is producing electricity, it will immediately generate heat and the cooling energy. So we have to consider this coupling property. And then these two stages should be coordinated in a mathematical way. Okay. Now, these formulas look quite overwhelming, but generally, you may also need to understand the principle behind. The principle is when we operate, when we dispatch this multi-energy system, we want to minimize the total operation cost, right? This operation cost comes from the fuel cost from the microturbine, come from the power import cost from the main grid, right? We want to minimize this operation cost. And our controllable, dispatchable elements or components are microturbine, chiller plant, electrical boiler, okay, and energy battery storage, thermal energy storage, and the fuel cell. These are all dispatched by us. But we have to satisfy the electricity load and the thermal and cooling energy load. So these all kind of details are mathematically modeled in these equations. So for this course, you don't need to fully understand these equations because there is not a need to do so. They are already listed in this paper, unless you are doing kind of academic research or research development. You don't need to fully understand the equations. However, you should understand the general idea. Okay, the general idea behind the multi-energy system, which is one realization of the energy internet. Okay. Then next, I would like to quickly show the simulation results to give you a better understanding of the multi-energy system dispatch. Okay, as I said, the different energy carriers, they have different properties, right? The thermal energy, they have much larger inertia and a much slowing responding transmission speed. But electricity is different, right? Electricity has the highest transmission speed and the lowest inertia. Okay, so what we do is we want to dispatch the thermal energy storage at the first stage, And we want to dispatch its on and off status of the CCHP plant, the microturbine plant. And we also want to dispatch, charge and discharge the energy storage system, because energy storage system, they also need to have a time coupling property. So we dispatch all of these three, two elements in the day ahead stage. That means 24 hours ahead, we want to decide the on and off status of the CCHP unit, the microturbine. And also we want to determine the charging and the discharging status of the energy storage system before 24 hours. Okay? But certainly we need to have the forecasted power demand, thermal energy demand, power output of the renewables as input. So we need to do the forecasting beforehand. And this forecasting can come from, let's say, forecasting software or even the forecasting service provider. Okay, so we have specific technique for the forecasting. Now, after that, in the intraday, okay, after 24 hours ahead, when we decide these variables during the realistic day, during each hour, we have to redispatch. We have to redispatch the power output of the CCHP. Okay, because the day ahead we only decide its on and off status. Okay, we don't dispatch its power output. Now during the intraday, the power output is re-optimized. It is re-optimized. Then these two stages are actually coupled together in the previous mathematical model. And then we can solve it using the commercial solver or our own solution algorithms. Then we can decide the dispatch results as shown here. Okay. On the first figure, top figure here, this is the first stage dispatch result. You can see this is on and off status of the CCHP. Okay, and the meantime, I'm also showing the power output prediction of the wind and the not the wind, sorry. This is the output of the micro turbine and the thermal generation units. The heat storage and the SOC, state of the charge of the batteries and the energy storage system. So these are day ahead dispatch result. And in the bottom figure, this is the intraday dispatch result. Okay, you can see a different the power output of the wind and the solar and the power exchange of the multi-energy microgrid with the main grid. Okay, you can see that all the results are showing there. Okay. Now, you may wonder, how can we evaluate the performance of your dispatch results? How can we assess whether your dispatch result is sensible or doesn't make sense? Okay, so here we have to compare this two-stage dispatch result with the traditional single-stage dispatch result. Okay. Now, just to give you a quick idea, okay, because our objective is to minimize the total operation cost, right? So we have to compare the operation cost of our dispatch result against the original dispatch result. But in the meantime, remember, we have to make sure that when we dispatch the generator units, we need to make sure the voltage and the branch power flow, thermal flow, they are not violated. They need to stay within the operation limit. So that's why in this mathematical model, we have these constraints. You can see here, we have different constraints. Okay. So in addition to compare the operation cost, we also need to compare the voltage violation rate. In other words, strictly speaking, we should make sure that there is no voltage violation. Otherwise, it will trigger the protection and lead to the outage, right? So here you can see we are comparing our method and the other existing three methods. For the first two methods, you can see although they have the averaging cost is relatively lower, however, they have a very high voltage violation rate, 30%. In other words, 30% of the buses are beyond the security limit. Remember yesterday I talked about the security, right? We should maintain the voltage within the limit. Now, for the third method, third method is another two-stage approach. However, you can see, although it can satisfy the voltage constraints, however, compared with our method, you can see it has a relatively higher operation cost. And our method has the zero voltage violation as well as a very low, almost compared with the method 3, a lower operation cost. So that's why my point is, by coordinating these two stages for the thermal resources and electrical sources, we can well operate the system, multi-energy system, and satisfy the operation limits and in the meantime, minimize the total operation cost. So that is my major objective in this approach. So this is actually one of the realistic realization of the energy internet. So I want to give you a sense that how, in practice, we can realize energy internet. We can couple the power grid with the thermal grid together and dispatch the CCHP unit. And on the other hand, we can also combine the power grid with the transportation network and dispatch the electrical vehicles charging and even discharging times and the power amount. That is another realization of the energy internet. Okay, so today, I only give you this case because in Singapore's context, we are more concerned on the cooling energy demand. That's why the coupling of the thermal network and the electric network are so important for us. All right, I think that is the end for this energy internet section. Okay, we still have 15 minutes. Let me go back to the students' questions. I can see some no questions typed in the chat box. Okay, so if you have any questions, you can raise here. We have 10 minutes to answer. Okay, one question is, what are the major challenges faced by multi-energy? Okay, I think the major challenges I just described is the different properties of the different energy carriers, right? Electricity, we have the light speed transmission of the electricity, and we have a low inertia. But the thermal energy network, they are transmitted at a very low speed. So how can we coordinate with different properties? This is one challenge. And if we are considering the coupled transportation and the power network, now you can see that the transportation network is substantially different, right? When the vehicle is driving on the road, it has many different properties, right? The congestion, the traveling speed, the routing target. Sometimes the vehicle will go through different roads, and these vehicles need to charge the power electricity at different locations. Sometimes it can charge in his company, the owner's company, or charge at the owner's own property. So the charging power will be very kind of diverse in both time dimension and the geometric dimension. That is another challenge. So I think the major challenge comes from the different properties of the multi-energy systems. And what are economic barriers to implementing multi-energy on a large scale? A very good question. If we consider, this case happening in Singapore, the multi-energy system considering both electricity and thermal energy. It's difficult to implement at a large scale because the thermal network is very expensive and difficult to implement. And also the thermal network will have a higher energy loss over long distance. Right? You can imagine that, okay, for our Singapore case, we have a district cooling in our CBD area. That area only covers maybe 2 times 2 kilometers. For that small area, yes, we can implement this thermal pipeline. And we can, tolerate this thermal energy loss. But for over long distance, let's say 10 kilometers, 20 kilometers, now the energy loss could be a significant concern. That's why here in the multi-energy system, we mainly consider the district heat network at the district level. Okay, and also the investment cost, sorry, is another concern. How do multi-energy market ensure system stability during sudden demand spike or supply factor? A very good question. So for this stability issue, we have to separate into different subsystems. For power system, the stability mainly comes from the voltage, frequency, and rotor angle, right? So for this one, we have different criteria. But for the thermal energy system, actually, it also has a stability criteria. That is concerned on the so-called supplying capability of the thermal pump to the load. If the system, have a disturbance, for example, outage of the pipeline, the heat energy cannot be transmitted there. Then we have to do a kind of network reconfiguration. We have to reroute the heat from one way to another way. And this will take a longer time. But this is substantially different from the electricity network. So when we analyze the stability, we have to separate them together. I think that is a major difference. Yeah. Okay, another question: is there a different response time between some and does this make cognitive? Yes, this certainly is. Their responding time are very different. That's why we design such a two-stage approach, right? We design this two-stage approach. You can see that in the first stage, we dispatch 24 hours for this slowing responding unit. And in the intraday stage, we dispatch every hour for the faster responding elements. So these two types of the elements, they can coordinate it together. But mathematically, we have to be careful. We have to be careful to model these two stages so that here you can see we are actually doing a two-stage stochastic optimization model. Okay. Now, the details could be very overwhelming, but general idea is that we need to disaggregate these two types of the units. And in the meantime, we have to mathematically coordinate them. That is a kind of challenge.
Any other questions?
Any other questions, please?
Professor, how about the power in your project? Power levels of your different renewable energy sources.
Which project?
In this REIDI's project.
Yeah, other project. Yes. This project. We have many different objectives. We have many different objectives because this is a very big demonstration project. So today I just introduce a multi-energy system part. For the whole project, here I can show you. This is a major research topics. Okay. Control, coordination, communication, data analytics, energy management system, microgrid optimization, power grid dynamics, and power electronics, the converters. So our colleagues are doing new types of the power converter topology for this special case. And some colleagues are also doing solid state transformer, SST. Yeah, which is advanced version of this, voltage transformation. And besides the energy economic modeling, energy trading. Okay, energy trading is very important, especially in my group. Recently, we are doing energy trading as well to participate in the wholesale electricity market. Yeah. Okay, so how can we model microgrid? Yes, we can use, if you are doing the dynamic study, you can use MATLAB Simulink. Yes, we are using Simulink to do the electric microgrid. But for thermal energy system, we can also do our own model. So for the thermal system, like this, wait a second, like this, this district cooling, okay, district cooling model. This one we are doing it in MATLAB. We're doing it in MATLAB. This one can be modeled in the MATLAB. Yeah, so that is not the issue. And besides, you can also use Python. Okay, you can also use Python because finally the operation becomes optimization problem, right? You can model it in Python, and there are a lot of Python libraries, toolboxes to solve this model. Okay, one more question. Is multi-energy affected by power system? Yes, certainly yes, because multi-energy microgrid, we have electric grid, we have thermal grid. The electric grid is certainly affected by the inertia, Yeah, but for the thermal grid, is not. Thermal grid, the inertia is very big. The transmission speed of the heat flow are not that fast. So that part is okay. Okay, another question. Yes, that we discussed on site. China was working global on the internet. Is more or less power centralization. If any blackout, does it may affect the order? Okay, this is a very, very good question for the global energy internet, global energy connection. Okay, I can tell you some ongoing happening projects. You give me 1 second. I will show you one of the project happening in Singapore, because in Singapore we don't have resources, we don't have coals, we don't have natural gas. Actually, we are importing oil, source oil from Middle East, and then we do the refinement. Here in Singapore, and then we can use the natural gas to generate electricity. This is how Singapore is surviving. Okay, so let me show you global version of a energy connection, energy system connection. This is a very ambitious project. Give me 1 second. I will open the website. There is in Singapore, there is a national strategy to import power from neighboring countries, and to do the regional grid operation connection. So here, let me show this news to you. Can you see the screen? You can see the screen, right? Okay, so here you can see Singapore. This is a Straits Times, the news journalist. Singapore plans to import 30% of energy from neighboring countries. So what we are doing is we are going to. This is announced by our ministry in a kind of conference event last month, October, 2 months ago. So you can see that we are going to actually connect our power grid with not this article. We are going to connect our grid with Malaysia and Indonesia. Malaysia and Indonesia. Let me. Okay, not this. There is a graph, actually. There is a graph. I need to find this graph first. So idea is Singapore is going to connect our grid with neighboring grid in Southeast Asia region. Yeah, so this, I can show this grid to you. Yeah. So here you can see this is Singapore, Malaysia, Indonesia, Vietnam, Cambodia. So we are going to connect our grid with a neighboring grid so that we can import clean energy. Because in Singapore we don't have much land, we don't have space to build solar farms. So your question is correct. If we connect with a neighboring grid, when there is a disturbance happening outside, it will certainly affect us. So we have to consider this contingency. We have to place reserve. We have to have our own backup sources. So at this moment, the government agencies, they are planning for this. So here in the locally, we need to place more power reserve. We may need to install more energy storage system to compensate if any outage happen outside the grid. Yeah. Okay, now next question, how uncertainty R and X manage in network model. Okay, so basically the R and X, theoretically speaking, they are also uncertain because the values depends on the temperature, right? The resistance depends on the temperature, depending on mainly the temperature, and also let's say if there is rain, if there is weather changes, R and X may change. However, this variation range is very small, so practically we can just assume it to be deterministic. Yeah, but if we want to consider it as an uncertain variable, that is also possible. That is certainly possible. We can just model it in the stochastic programming. So that is certainly possible. Compared with the renewable power output uncertainty, the line parameter uncertainty is not that much. All right, any further question before we finish this morning?
I think, yeah. Thank you all participants.
Okay, thank you all participants. Then in the afternoon, I'm going to introduce the smart metering. Okay, let me show here. In the afternoon, I'm going to introduce advanced metering infrastructure and the smart meters. Okay, they are all, key technologies for the smart grid. Okay. Okay, all right. I'll see you later.
Yeah.
Bye bye.
Thank you, Professor. Bye-bye.
Thank you.